Oh, good afternoon. I'd like to draw your attention again to they're quite formidable, but it's epoch-making, one way to say, book, monograph by Alain Kahn, Non-Commutative Geometry. It has enough research suggestions in it to keep someone busy for a lifetime. And at the same time, it's it's a masterpiece of popularization, I would say. Well, some of you may have noticed that if I'm delayed a minute or two now, it's because I just sent out an email making my presence unnecessary, perhaps. I mean, just saying what we have to do today, and if once you know what we have to do, I think it's so natural. This course is so natural that you can just do it. You don't need any help. Okay, well that's one. I think that's one approach. One way of approaching the subject. It's I think it is very natural. Now, well, this is roughly not quite, but it's getting close to 100 years since modern K-theory was discovered. It actually goes back thousands of years, I mean, to linear algebra, because the basic theorem in K-theory, and one way of stating the basic facts of linear algebra is just that as a group, the abelian group of which is K arises as K0 of a field, any field, is what on the left? Yeah, would you remind me what your name is, please? Justin. Okay, you're Justin. Okay, and what is the K0 group of a field? Yeah, right. The group sometimes is written as with blackboard bold Z, right? Yeah. Can you prove that? So taking as for the definition of K0, we can take a simplified definition. You take the finitely generated vector spaces, okay, over the field, and then you turn them into a semigroup by taking direct sum, and that's an addition operation, right? But and it's not quite abelian or associative, right? Because an apple and an orange with apple called number 1 and orange number 2, that's not the same thing as an orange and an apple, right? On the other hand, if it's two oranges, if it's two electrons, then they're indistinguishable. That's one of the basic principles. How many people have run into that? Okay, good. That's so in this course, two vector spaces with fake dimension 10, meaning the smallest number of generators is 10. We will consider them as being indistinguishable. Okay. In other words, we will look at the isomorphism classes of finitely generated vector spaces and turn them into a semigroup. Okay, an abelian semigroup. And every time you have an abelian semigroup, it has a 0 element, so it's a monoid. Then you have an enveloping group. Okay, and this is even the very oldest case of the enveloping group construction, because the semigroup, Clarissa, what is the semigroup? What do we get? What do you have? Do you remember? Have you done the calculation? What you get for the semigroup? Okay, the monoid. I mean, you look at the finitely generated vector spaces over a fixed field. then what is the and you look at direct sum and isomorphism, which is compatible, so sum of isomorphism classes. This is an abelian semigroup, right? With addition. Does that make sense? Well, okay, so you're not familiar with the definition, but probably sooner or later everyone should know what a semigroup is. It's because it's for one thing, it's the progenitor of a group. It's like if you have whenever you have a semigroup, you get a group. And if it's a semigroup of natural numbers with addition, what's the group? Yeah, okay. And all right, so but that's the fundamental. That's equivalent to any other non-trivial fact in linear algebra. Okay. It's non-trivial. It itself is non-trivial, but it implies any other non-trivial theorem. And for instance, the uniqueness of a number of elements in a basis, if it's finite. And okay, but you know, I really would like people to jump on linear algebra and look at all the non-trivial theorems and start to show that they're equivalent in trivial ways. This is fair game for exercises. Okay. Even an essay, if someone wants to blow the whole subject of linear algebra out of the water, okay, somehow expose it, okay, as just a single theorem, together with a theorem saying it is just a single theorem. Okay, that's my fundamental theorem. That's what I like to think of as my fundamental theorem of linear algebra. That all the basic first order non-trivial theorems are equivalent, in fact, in a trivial way, okay? So for instance, if you have finite dimensional vector space, finitely generated vector space, you look at the dual space, then there's a one-to-one correspondence between linear operators on one and linear operators on the other, which interchanges injective and surjective, okay? That means that gives you a trivial proof. This is an easy fact. It gives you a trivial proof that the theorem injective implies surjective is equivalent to the theorem surjective implies injective. Because of the exchange, the interchange. Again, it's like quantum mechanics. It's interchange, okay? But it's like the anyway. Okay, that's an example of the fundamental theorem of linear algebra. That non-trivial theorems are trivially equivalent. And how many? Maybe if there are 14 non-trivial theorems in linear algebra, and as I said, not counting canonical form. It's just the things that are basic for an arbitrary field and don't use ring theory, just theory of the field. So if there are 14 of these non-trivial theorems, then how many trivial equivalences are there that we have to check? Well, I guess it's the number of ordered pairs among 14 elements, right? So a fair number. So that, you know, let me go back to grade 10 or whatever it was. Is that 14 times 13? Okay, but you know, I could go back even farther and say that from my multiplication tables, I know that's such and such a number. But we never took our multiplication tables more than up to 12 by 12, 12 times 12. So I don't know 13 times 14. But you all will know that. Okay, good. But that's so that's a good essay, right? That's a pretty good essay. Keeps you busy for a while. Well, no. As soon as you do 2 or 3 such trivial equivalences, I think this will confirm in your mind the idea that linear algebra is just a single theorem, a single fact. It's a single fact. Okay, and a bunch of much easier facts, for instance, the existence of a basis. Okay, but so and in this approach, we defined give the simplest definition of K0 in this setting. We looked at certain modules and treated them in an obvious way. Direct sum and isomorphism. Now, there's another approach which is gives you K0 for a unital ring. It's called the idempotent approach, and we've been discussing that from time to time. It's what's done in the book. And it's just a little more computational, but it has advantages. For instance, if you have a map from one ring to another, then it's easy to see that an idempotent element goes into an idempotent element. So that's why it's a function, okay? And equivalence goes to equivalence. That's in terms of the Murray from the equivalence of idempotence. That's just so that's so that's whereas if you do it with modules, one advantage for doing it with modules is it works for arbitrary modules. Okay, you don't need to look at the modules that correspond to K0 idempotent. So what are the what are the modules? Remind us of the modules that one looks at in defining K0 for unit. Okay, but that's true if it's over if the ring is a field. But in general, you want the module to be a direct sum of a free module, a direct summand of a free module, right? Okay, so that's called projective. There are lots of, in general, there are lots of non-projective modules in general. And so if you take arbitrary modules, say finitely generated modules over a ring, then then the semi-group that we talked about, isomorphism causes with the natural addition, this is a functor, okay, from rings to Abelian groups, okay? It's not the K0 group in general. But okay, so that's one advantage, okay. But so that may be, I just wanted to touch on this today because it's an ongoing project, I feel like, understanding the definition of K0. But one basic, and of course, the question is if modules correspond to idempotence, then equivalence of idempotence is supposed to correspond to equivalence of modules, right? If they are the right kind of modules, projective and finitely generated. Okay. Well, it just turns out that, well, we've already said it, the isomorphism of a module is equivalent to equivalence of the idempotence in the Murray van Emmen sense, described in the textbook. And well, also if you look at idempotence, you look at, since matrices come into the definition, if you look at idempotence in matrix algebra, that means that if you take matrix algebra over a ring, then it will have the same K0 group. The semi-group will be the same. Whereas for modules, you have to work with it because it's the same. But again, the advantage is that it's true for arbitrary modules. Okay. Well, let me just as I put in my email a few minutes ago, before arriving, before coming here, has anyone taken the time to take a look at it yet? I mean, taking the time off from class, as it were, take a look at the email. Well, I don't expect it to be such a cliffhanger. Okay, we will look at it rather than listen to me talk. Okay, but I put in a simple elementary exercise which should help elucidate the problem of what isomorphism between modules, how that corresponds to equivalence of idempotence. Okay, so here's the general exercise, and I suggest to look at it for a field. Okay, just to start with a field, say, of complex numbers or the rational numbers. So you have so you look at not an isomorphism, but not between two general modules, but an endomorphism, okay? And the special module, if the ring is if the ring is the ring R with a unit, okay? Then the module is R. We talked about left modules, I guess. Well, we can talk about left or right modules. And again, a priori for arbitrary, for passive arbitrary modules, it doesn't, I don't know that left will give you the same as left modules will give you the same group as right modules, okay? But if it's projective, finitely generated projective, then it does. And that, the proof of that I know goes through idempotent. So that's a good exercise, I would say, to understand what's going on. Okay, so this is the left module R, okay? It multiplies on itself, multiplies itself on the left. So we consider it as vectors and as scalars at the same time. The ring element, which is a vector, gets multiplied on the left by the ring element, which is a scalar. Okay, and so the question is, suppose, what are the homomorphisms? That module homomorphism from this ring into itself. It's sometimes called the endomorphism. Homomorphisms with two different modules, and this is Greek, okay? It's not Greek to me because I studied high school. In high school, I studied a bit of Greek. Our Latin teacher gave a Greek class for 1 year at lunchtime. Okay, but here's the endomorphism, and a good question then, good elementary exercise. Well, good warm up for this modular approach to case theory. It's the same as the idempotent approach. Okay. What's the question? The question is, what is the endomorphism ring? Okay, it's a ring. It's composing, and you can add them, adding them like linear transformations on a vector space. Linear transformations from a vector space into itself, that's an example of endomorphisms, right? And if the vector space is one dimensional, which is the scalar field, what are the endomorphisms? How many endomorphisms are there, Daniel? If you have just a one-dimensional vector space, then what are the endomorphisms? The linear, that means the linear transformations of it into itself. Well, 0, an identity, but that's true for any vector space. But what's especially simple about the one-dimensional case? Of course, if I said the 0-dimensional case, it would be obvious, right? We've got a complete list already. In fact, the 0 and the identity of map are the same. No. Right? Any wish? All right. Well, yes. Well, the 0 is allowed because we're not asking about isomorphism. It's just not asking about automorphism, but endomorphism. So 0 is allowed. The identity map is, of course, allowed. But what else do you get? If it's, say, the field is the complex numbers, what's an example of a linear map for the real numbers? If it's the real numbers, what's the example? What's the graph of a linear map from the real numbers into itself? What does the graph look like? If you draw the graph in two-dimensional space, what does it look like? It's a straight line, right? Okay, but then the straight line has a slope, right? Well, and that's a real number. Well, I guess that's the linear transformation, multiplying by that real number. Okay, and so I guess in general, if you have a field, the endomorphisms are multiplying by an element of the field. And if it's a two-dimensional vector space, the direct sum of two copies of the field considered as vectors, then the endomorphism ring, Rishi, what's the endomorphism ring? Yes, everyone agree with that? Charlie? That ring a bell? Okay. No, but I'm just trying to get people to ride this like a favorite horse, okay? It's I mean, linear algebra because that's what this course is. It's glorified linear algebra with a bit of calculus thrown in. Don't quote me on that. Of course, I'm broadcasting worldwide, right? All right. What would be the anyone want to just blurt out? Well, that's maybe not a very good way of saying it, but anyone want to say immediately what the answer is for the arbitrary unitary ring? Yes. Okay. How many other people? Rishi, he's ready to jump off the. Well, but yes. Remind me of your name, please. You're Jack. Okay. It's a little dark. My excuse is it's just slightly dark over here at the edge, well, it's getting less dark all the time, I must admit. But I mean, I'm getting a little more familiar with this people's names. Okay, so Jack, what's the answer? Exactly. We just decided that's what it was for a field, right? Okay, and it turns out that for any unital ring, if it's not unital, then it's a more challenging question, okay? But if the ring is unital, then it's a very good exercise to prove that just like for a field, you get the ring itself. Multiplying on the left, it's non-commutative, so you have to multiply. Oh, I'm sorry, it's a module on the left. And the endomorphism is supposed to commute with multiplying on the left. I guess that means it's going to, so it's isomorphic perhaps to R, or maybe to the opposite ring. Okay, have to be a little careful. Have to reverse the product maybe. That's a good exercise. Okay, what is it? Okay, and of course it's and the element of the ring. You have to say how it acts as an endomorphism, right? It's going to not be multiplying on the left, is it? In the non-abelian case. And so what's it going to be doing? Well, yeah. Well, in the commutative case too, but you wouldn't notice. Yeah. And it's you're very careful not saying on the right side, because it is the right side, but it's also the side which is called the right side. Okay. Sorry. Okay. No. Okay. So you could say R, and you might better say with some right multiplication. But then maybe is it R or R op? Okay. Op means the opposite ring, where you instead of model for x times y opposite is y times x in the original sense. Okay. So and this is something that I have to keep. I don't have it at my fingertips 100%. Okay, but I'm aware of the possibility. I'm willing to bet even money that it's the opposite. Yes, Jack? Yeah. So that's still a ring. And yeah. And the unit is still the unit. And the 0 is still the so on. Yeah. Okay. Yeah. So that's a very important concept because in our course, C2 algebras are going to be non-commutative rings, right? So when Professor Kahn says non-commutative geometry, that's his term in this sense. I think in algebraic geometry there's a somewhat related term. Yes. Are you? No, please let me guess. Are you Abu? No. Okay, Sadek. Okay, how's that? Okay, if I can get everyone with one mistake, I'd be happy. Okay. So Sadek, what is your question? That's a very good question, and the answer is no. Okay. And in the setting of phenomenon algebra, people have written technical papers constructing examples where it's not true. Okay, and the same for C-star algebra. Now, one reason I don't have these samples at my fingertips is I concentrated on what are called classifiable feature algebras, or simple invariants, including the K0. It's a class which can be for which the K0 functor and related things, K1 and traces, actually tell you what the algebra is, okay? And that's true for the UHF algebra too, by the way, but that are included. But the classifiable ones, because the invariant, which determines the algebra and isomorphisms between the invariant, come from isomorphisms between the algebras. That means that if there were something not isomorphic to its opposite, then the invariant would not be isomorphic, okay? And if it's non-abelian groups, then a group can be not isomorphic to its opposite. I don't think the map to the inverse actually that is an isomorphism with the opposite. Okay, so what I was going to say was that the invariant is, if you look at the invariant, then it doesn't distinguish between an algebra and its opposite, okay? And one way to say that is we've already seen a glimpse of that with the definition of K0 in terms of idempotent. So the left module construction and the right module construction of K0 are the same, okay? So, of course, saying that the group itself is invariant to its opposite, that's not really enough. You want to know that the full invariant. Anyway, the answer is that the classifiable ones are all isomorphic to their opposites because they're true at the level of invariant, okay? And but the non-classifiable ones, well, if you're going to classify them to some extent, you've got to introduce a non-mirror symmetric invariant. And so that hasn't been done yet, okay? But, okay, no, very good question. Okay, so okay, so this was supposed to be just a brief sort of flashback recap. So gradually making headway into understanding what K0 is. But now I want to talk about one of the fundamental, one of the basic discoveries that led to the development of operator algebra theory to its present extent. Okay, so namely the Glim's PhD work, and what Glim proved that the UHF algebras, infinite tensor products of matrix algebras. I will keep recapping on what the definition of this is, okay? But I think the terminology it would be nice if people start to accept the terminology as a reminder of the objects, okay? What the objects are. So it's a tensor product of two things, two matrix algebras. It's isomorphic to another matrix algebra, right? You multiply the orders of the matrix algebra. That's a good exercise, by the way, to check that. Have you taken a look at that, Marissa? So M2, it seems to me we might have been discussing this at some point. M2, tensor M2 is itself a single matrix algebra as an algebra, okay? And you can check which one it is by just calculating the linear dimension. Right? And that's 16, right? M2 is 4, dimension 4. M2 is dimension 4. 4 times 4 is 16. And what's the single matrix algebra that has has linear dimension 16? Well, you have to take the square root of 16, and it's not just a coincidence that 16 has a square root, okay? Because it's the tensor, because it is a matrix algebra. This is a basic fact which explains why certain numbers have a square root, okay? There are other cases of that. Using quaternions. Quaternions are very good to show that something about sums of squares. Has anyone seen that? Okay, we should just look it up. Quaternion sums of squares, okay? But I mean, that's a different, I think that's a different sequence. Charlie, have you run into that? Okay. But, well, so so 16 is 4 squared, and if it is a matrix algebra, then it has to be M4, right? Okay. That's not a proof that it's M4. It just is a suspicious coincidence. Okay. Sometimes you can just work that way in math. I'm especially happy if I can make some progress conceptually just by noticing something fishy. Okay. Occasionally happens. Of course, sometimes it's me that's a bit out of kilter. Okay, so finite matrix algebras, the tensor product is another one. If it's infinite tensor product, then you don't get a ordinary matrix algebra. You get an infinite dimensional GLIM UHF algebra. Okay, and just an algebraic version of it that's as good as we need to look at for basic ideas. GLIM also made a big contribution to C-star algebra, to functional analysis C-star algebra theory by mastering the C-star algebra completion analysis of this classification. Okay, there are a lot of techniques that we introduced, but the basic algebraic and k-theoretical content of the subject comes at a purely algebraic level. You look at the finite tensor products, which are as algebras, and if you add more and more finite dimensional matrix algebras, and you get larger and larger algebras, you just take the union, okay? Don't bother completing it. And you don't have to worry about the star operation for the classification. In general, you do, I guess. Okay. But, so that's what we're trying, that's what we want to study. And GLIM had his way of doing it. Dijkstra found a particularly elegant way of doing it. It's just of stating the theorem, okay, which is based on a number theoretic, fundamental number theoretic study. Well, a basic number theoretic observation, okay. It's number theory, but I don't think it was familiar in number theory, okay. I would say Dijkstra discovered a new property of rational numbers, okay. And what was it? Well, I outlined it in this famous email. I hope it goes through. Has anyone received it? Sometimes it takes a while. Okay, but anyway, so you look, on the one hand, you look at the field of rational numbers. Okay, and so it's going to feel like it's contained in R, but that's it exists in its own right. We're just considering it as we're not considering it topologically, okay? So let's not worry about it being contained in the real number. It's just a group, okay? It's a group. It's a vector space, so it's a field, okay? But we're thinking of it at the moment just as a group. And suppose that you look at the subgroup. So if you have a group, then it has subgroups, right? Suppose we look at subgroup, and just to simplify things, let's not look at an arbitrary subgroup. Let's look at one that contains the number 1. Okay, sort of to center it. All right. So we're looking at subgroups of Q containing the number 1. So the zero subgroup is not allowed. Okay. But is the integers allowed? Is the group of integers allowed? Charlie? Okay. And are there other finitely generated groups that are allowed? The group of rationals is not finitely generated, right? It's not a finitely generated. It doesn't have a finite set of, doesn't have a finite subset. It generates the whole group. That's a good exercise. But we have lots of finitely generated subgroups. But how many people are familiar with the fact that if you have a finitely generated subgroup of the integer, then it is generated by a single element. It's singly generated, just like the integer. Okay, that's, in fact, it's isomorphic to the group of integers. Well, that's not a, once you know it's singly generated, that's not a mystery. So you have subgroups that are isomorphic to the group of integers, and then you have the ones that are not. Well, it's the ones that are isomorphic to the group of integers. It's easy to describe those. You just take 1 over n times z, where n is equal to 1, 2, 3. So n is a natural number. Natural number. Okay. Well, what have we been talking about the last few days, last few meetings, besides natural numbers? But not if you don't get into algebras, what have we been talking about? What's one thing we've been talking about? Well, it's a slight generalization of, well, it's maybe a hefty generalization of the natural numbers, right? Daniel? There was even a sort of slightly cute name for them, right? Jack, have you looked at them? I think I might have stated last week that there's a natural topology on the supernatural numbers, which turns them into a Cantor set. You include the natural numbers among them, okay? Because it's sequences of exponents, sequences of exponents, and have an exponent sequence that tells you what the power, which power of which prime number you should take, okay, from 0 up to infinity. The 2 to the infinity is an example, and if n is 2 to the infinity, that a supernatural number, this expression 1 over n times z still makes sense. And if all the exponents are infinity, then what is 1 over n times z? Anyone want to do a lightning calculation? It's a subgroup of Q, okay? So what is it? Well, yes. Sorry? Is that a group? Well, okay, I'd say it's not bad for a first guess, okay? And I asked for it by talking about lightning calculations. I mean, seriously, that's the way. Just keep thinking about it, okay? So we're looking at all possible subgroups of Q containing the number 1. But I guess I should have said containing Z, okay? It's a subgroup, so it contains Z, all right? Contains number 1. And so the largest one is the smallest one. The smallest one is Z. And then if n is that's with n equals 1, right? Then if n is equal to 1, the supernatural number is equal to 1, then 1 over n times Z is Z, and that's this case. So that's where you have the smallest exponents, 0 everywhere for every prime number. But suppose the exponent is infinite for every prime number. Then I guess that's the largest supernatural number, right? So I guess it should be the largest subgroup. What's the largest subgroup? Sorry? Yes, good, thank you. You know, this room is not that bright yet. So I would say that if you make a lightning calculation and it comes out not perfect, don't hold back from expressing it, okay? Expressing the answer, because I might not remember. Okay. Okay, so, but I think you get the picture. So here's an exercise. If n is an arbitrary supernatural number, what's the subgroup? Okay, so if n is, if it's 2 to the infinity, 3 to the infinity, 5 to the infinity, and so on, then the subgroup is Q. And if n is, if the supernatural number n is 2 2 to the 0, 3 to the 0, 5 to the 0, and so on, then that's the subgroup Z, right? Okay, so anything in between is going to be, Dixmay proved that it was an arbitrary subgroup, okay? That was coming from an arbitrary supernatural number, and they have to prove it, right? So that's an exercise. I would say that this whole circle of ideas could be viewed as an essay, a serious essay, okay? And this is without getting into C-star algebra yet, without getting into infinite tensor products, algebra, C-star or algebraic of purely, in this setting, purely algebraic is fine. And so without, even before we get into that, we're just sort of warming up to Dixmay's approach to William's work. This is in fact, if you ask your favorite number theorist, does he know this? There's a one-to-one correspondence between, if you ask him about singly generated subgroups containing Z, then he would tell you immediately that it's 1 over n times Z, where n is a natural number. Probably any high school student could tell you that. Okay, do high school students know what the rational numbers are as a group, and the subgroups of rational numbers? They know what the integers are. Or, sorry? Well, I think I did. I'm just always assuming that people know more and more all the time. Yeah. It seems that way anyway. Yeah. Okay. Well, so even without mentioning C-star algebras the whole day, yes, Charlie. Yes. Well, you said that, I think. Yeah.
I said that too.
Well, I said it. I just concurred. So we may have to keep checking our work, right? Okay. Did you study Greek? Okay. How many people study Greek? Yes. So what's the name for it? When the supernatural number is 2 to the infinity. So what's the subgroup you get? Wait, no. That's when it's all the exponents are infinity. If just a single, if all the rest are 0, so you don't have any factors of any prime numbers except 2, then yeah. So a dyad is something to do with the number 2, and it's a dyadic numbers. Okay, it's usually they're considered as a ring because they are a ring, but not every subgroup of Q is a ring, of course. That's a good question. When is a subgroup of Q a ring? Well, I guess it's when, if all the exponents are infinite, you get Q. If all the exponents are 0, you get Z. Those are both rings. Maybe all the exponents have to be, and so if it's 2 to the infinity, then the exponents are all 0 except for 1, which is infinite. I suppose if okay, so here I'm doing a lightning calculation. I hope that's wise. The question is, when is the subgroup closed under multiplication, right? Well, I guess it's when anyone want to, yeah. Well, why just, yeah. So as long as the only exponents, if all exponents are 0 or infinity, then you have a ring, if and only if, I guess. Okay. And by the way, interestingly enough, this turns this group, by the way, is the K0 group, okay, of the UHF algebra corresponding to this supernatural number. And the number 1, the number 1 is the class of the unit. It's a normalized calculation. The algebras are unital, and the K0, if it's idempotent, you have the special element 1. that special idempotent one. If it's modules, you have the special module consisting of the whole algebra. Okay, so in either case, these are the K groups of, either way you look at it, these are the K groups of Slim's UHF algebra. And that's what Dijkstra sort of noticed, okay? So he said, if you can get the group, there's a one-to-one correspondence between the groups and the supernatural numbers. And the supernatural number, by the way, is exactly the data of the UHF algebra. If you know the group, for have two UHF algebras and they have the same group with the same inclusion of the integers, same both containing one, the same group, then they have the same supernatural number, so they're equal. They're exactly the same UHF algebra, infinite tensor product of prime power order matrix algebra. Okay, so this is the once you understand this, then you have Slim's thesis, okay, which was the beginning of a lifetime of various important contributions to science, still going on, which at one point, I mentioned the presidential medal that he was awarded once. A number of people in C-square algebra theory have been awarded presidential medal. Maybe there's one every year in science, not so often in math. But also he was one of the people who. It's a considerable distinction to be elected the president of the American Mathematical Society. Well, also in Canada, the Canadian Mathematical Society. But, so Glim was the president of the AMS for a while. So was his colleague working on C-square algebras in quantum field theory, Arthur Jaffe. He was president of the AMS. I don't know if he got a presidential medal. I don't think he quite managed to attain that. But one of the main theorems in this course is called the Bott periodicity theorem. Well, 2 comments on Raoul Bott. He was educated here. He came from Czechoslovakia, I believe, in 1968, and a lot of people did. And the country was called Czechoslovakia. And item 2 is he's the for inventing the Bott periodicity theorem, for discovering it, he was awarded the Presidential Medal of Science. And for other work, but related. I think you could say his work is related to that. Well, all right, I think maybe other people waiting. So, any comments or questions? We could, if anyone wants to discuss something briefly, then well, for a while, then there's lots of space outside.